So today I will discuss about this about a numerical on Phi Index, effective rainfall hydrograph, and direct runoff hydrograph. Uh, it is to be noted that we know that what is Phi Index is. Phi Index is total rainfall minus Phi Index is total rainfall minus effective rainfall divided by incremental duration of the storm which has created that total rainfall and certainly the effective rainfall. Now you say, what is this one? Effective rainfall hyetograph. Effective rainfall hyetograph is a graph which shows the effective rainfall at its ordinate and duration at the x-axis. So basically effective rainfall is that rainfall when you remove initial loss and infiltration losses from the total rainfall. So if you remove initial loss and infiltration loss from total rainfall, you will get effective rainfall. And if you display it in a curve per 2 hour or per hour, how much effective rainfall has taken place, that becomes effective rainfall hyetograph. And in this case, you must remember that this effective rainfall will be actually effective rainfall intensity, which can be represented by the unit centimeter per hour. This is the standard unit, centimeter per hour, but you can represent it in millimeter per hour also, or any. But the time, the main thing is that it should have the time as the denominator. It should have in the denominator the unit of time, and in the numerator the unit of rainfall. Okay, so this is what is the effective rainfall hyetograph. And as you know, hyetograph is simple: rainfall intensity versus time from start of storm or duration of storm. So that is what is hyetograph. Now what is DRH? DRH is direct runoff hydrograph. It is the discharge per hour from start of the storm to the end of the storm duration. In the ordinate, direct runoff is shown. In the FCC or x-axis, duration is shown. So what is direct runoff now? You will say direct runoff is nothing but total runoff minus base flow. Direct runoff is total runoff minus base flow. And always remember, the effective rainfall is equals to direct runoff. And if you want to find the volume of direct runoff, then you have to multiply the catchment area with the effective rainfall or the area of effective rainfall hydrograph to find the volume of direct runoff. Okay, so I think it is clear. Phi index is total rainfall minus effective rainfall divided by the duration of the storm. Then or To be more precise, the duration of storm is incremental duration of storm. And ERH is the effective rainfall hyetograph. Effective rainfall means total rainfall minus initial loss and infiltration loss. H means hyetograph. Hyetograph is a curve which displays effective rainfall in the y-axis and duration of storm from start to finish in the x-axis. And direct runoff hydrograph is what is direct runoff? Direct runoff is the total runoff minus base flow, and hydrograph is that curve which shows direct runoff or runoff in the y-axis and duration of storm from start to finish at the x-axis. And remember, area of ERH multiplied by the catchment area will give you volume of DRH. Clear? So this much introduction is enough for solving the problem or numerical problem that I will discuss now. So the numerical problem is like this. Catchment area is given, duration of storm is given, Phi index is also given. Now the question is, what you have to find out, it is determine the effective rainfall hydrograph. What is ERH? I have already explained. And volume of direct runoff. How much volume of direct runoff has been produced due to that storm. And this is the table which shows the duration and accumulated rainfall of the mass curve of rainfall. Now, mass curve is nothing but the values of y-axis is incrementally summed. That means the first value is added to with the second value and then shown in the second value at the y-axis. So, and this is the mass curve is also shown as or referred to as accumulated rainfall versus duration of rainfall or time from start of storm to end of storm. And accumulated rainfall means you can see that this is actually 0 in the initial duration, 0th hour, 0 rainfall takes place, okay. Then after 2 hours, 0.6 rainfall taking place. After 4 hours, they are saying 2.8 rainfall, but this is not the effective rainfall. This is what? This is actually the summation of the rainfall that is taken place at the second hour plus the rainfall that has been taken place at the 4th hour. So actually this is a sum of 2.2 centimeter rainfall with 0.6 centimeter of rainfall, that is 2.8. Then along with this 2.8, when you sum 2.4, then you will get this, the 6th hour accumulated rainfall. But actually at the 6th hour, at the end of 6th hour, the rainfall that has taken place is 2.4 centimeter per hour. At that time you have to use the unit centimeter per hour because then it is given the rainfall per hour. Okay, and in this manner the rainfall of the earlier point is added with the rainfall of the present point and shown it. And in this way 14-hour rainfall is displayed in this plate. I think it is very clear what I want to say. The rainfall at 0th hour is added to the rainfall at after 2 hours and then shown in this y-axis. Then rainfall up to 2 hours is added to the rainfall up to 4 hours and then shown in the y-axis and so on. Okay, so catchment area given, duration of storm given, Phi index given. We have to determine or draw the effective rainfall hydrograph, and we have to find out what is the volume of direct runoff from this storm. Okay, so how to solve it? Look, as we know, I have already discussed about this in the first slide itself. This Phi index is nothing but total rainfall minus effective rainfall divided by incremental duration of the storm. Here incremental duration of the storm is 2 hours. Total rainfall has been given in the table as accumulated rainfall, and effective rainfall they have not given. So I can say that effective rainfall ER is equals to total rainfall minus phi into del T. So this is very simple calculation. Del T is taken here at the left hand side. So as del T is in denominator, it is multiplied with Phi index. And then this total rainfall has also been taken to this left hand side. So total rainfall minus phi into del T is your effective rainfall. But note down, if phi into del T is more than total rainfall value, then we will assume that ER is 0, because ER cannot be, effective rainfall can never be a negative term. It is very certain, because rainfall cannot be a negative term. So if it is a negative term, which can only happen is if 5 into del T is more than total rainfall, we assume that ER is 0. Okay, so now let us see how they have calculated the intensity of ER or effective rainfall, because this is required to draw the effective rainfall hyetograph. So what they have done is they have done a table, drawn a table. In the first column they have said time from start of storm. So this is the duration of storm from 0 to 14th hour. So the time interval, as you can easily see, 2 minus 0 to 4 minus 2 to 6 minus 2 to, so 2 hour interval rainfall. So the time interval is between 2 points of the FCC is 2 hours. Now let us see what is the accumulated rainfall part 2 hour. So that has been given in the first table in the question itself. So in the first 2 hours it is 0, then followed by first 2 hours it is 0.6, then followed by 4. This is accumulated rainfall, so 2.8, 6th hour 5.2, 8th hour 6.7, and so on. So I have already discussed about this. Now to find the depth of rainfall in del T duration, after 2 hours, now I am deconverging the accumulated rainfall into single rainfall data, because that is what we need, because we have to draw the hyetograph. Okay, not the mass curve of hyetograph, but only the hyetograph. So we show the rainfall intensity in the y-axis and duration in the x-axis. So how to find it? Just lag this data of this column. Okay, this column number 3, by 2 hours. So just leave this first row, okay, and write this entire data from the second row. You have seen 0 has been given here, 0.6 is there, 2.8 is there, 5.2 is there, 6.7 is there, and so on. Okay. Then you deduct column 4. Then you deduct column 4 from column 3. Column 3 is the original accumulated rainfall, and column 4 is the 2 hour lagged accumulated rainfall. 3 minus 4, column 3 minus column 4. You can see certainly that the single value rainfall intensity is now given here in this column 5. Because you can see that 0.6 plus 2.2 is 2.8. So originally after 2 hours there was a rainfall of 0.6. After 4 hours there was a rainfall of 2.2. But as we are showing a mass curve of hyetograph, so we are showing this 0, 0.6, 2.8, 5.2 and so on. Their accumulated rainfall in delta hours. Delta means incremental duration. For this case it is 2 hours. So after you deduct column 3 or column 4 from column 3, you get the single value or depth of rainfall per 2 hours that has taken place during the storm. Now I know that what is 5 into delta because both the values are given. Phi is 0.4 centimeter per hour. Delta, the incremental duration is 2 hours. So 0.4 into 2 is 0.8 and that is what it is written here. 0.8, 0.8, and so on. Now in the first area, this one, not first, equation number 2. See this equation number 2. Hey, what is effective rainfall? Effective rainfall is total rainfall minus phi into delta. So 5 into delta in our case is phi 0.4, delta 2 hours. So for all cases it will be 0.8. Now total rainfall depth is shown here in this column 5. Okay. So now what we will do, we will deduct column 6 phi into delta from total rainfall which is represented in column 5. So what will happen? Column 5 minus column 6 will give you the effective rainfall as per equation 2. Now note down that this equation 2 also have this condition that if phi into delta is more than total rainfall, so to avoid negativity, we'll assume that ER is 0. And surprisingly, the first case is like that, 0.6 is less than 0.8. That means 5 into delta is more than total rainfall 0.6. Clear? So to avoid negativity, we have write 0. But for the next case, in the second column, total rainfall is 2.2, 5 into delta is 0.8. So total rainfall is more than 5 into delta. So we have deducted the delta 0.8 from the total rainfall or depth of rainfall, whatever you may say. This is what is 2.2 and we get a value of 1.4, which is the ordinate of effective rainfall. Okay, and because hyetograph is rainfall intensity versus duration of time, the storm sustained, that is why what happened, we have to find the intensity of ER. How you can find the intensity of ER? We know that 1.4 centimeter rainfall, effective rainfall was there per 2 hours. That means after 2 hours, 1.4 effective rainfall was observed. So what will be the intensity? 1.4 divided by 2. So 0.7 will be the intensity, and this will also be the ordinate of the effective rainfall hyetograph. Correct? And you see the ordinate of the only effective rainfall was 1.4. After deducting phi into delta from the total depth of rainfall given in column 5. So 2.2 minus 0.8 is equals to 1.4. And then when I divide it by 2, we get 0.7, which is the ordinate of the actual effective rainfall hydrograph. Not actual, but effective rainfall hydrograph. Remember, in a hydrograph, always ordinate are the rainfall intensity. If it is total rainfall intensity, it is DRH. If it is accumulated rainfall, then it is ERH. But hydrograph always shows the intensity of rainfall in its ordinate or y-axis. And x-axis is your duration or incremental duration of time when the storm was sustaining. So 1.4 divided by 2 is 0.7, then 1.6 divided by 2 again, 1.6 divided by 2, 0.8. Then 0.7 divided by 2, 0.35, 0 cannot be divided, so 0. 0.9 divided by 2 is 0.45, 0 cannot be divided by 2, so it is 0. So all the ordinates, required ordinates of the effective rainfall hydrograph is we have found out. Now let us see how to. Yes, so this is the effective rainfall hydrograph of the storm. As you can see, the ordinate or y-axis is the rainfall intensity. This rainfall is effective rainfall. So this rainfall intensity is effective rainfall intensity, or many times we say it as ERI. So these are the graph. This is 0.78, 3.45. And remaining are zeros, there is no graph of them. Now to find the area of ERH, as you know that area of ERH, the first slide I have discussed, into catchment area, is your volume of DRH. This is your volume of DRH. So this volume of DRH is the second part of the problem. First part is we have accomplished. This is the hydrograph, 0.7, 0.8, 0.35, 0.45, and all these zeros are the ordinate of the hydrograph, represented in the unit centimeter per hour, because we are representing rainfall intensity, not rainfall. Always remember that for hydrograph, y-axis represented rainfall intensity, not rainfall volume or rainfall depth or simple rainfall, not that. This is rainfall intensity. For 1 hour, how much centimeter rainfall has taken place. That is what they represent in hydrograph. Now, if you deduct the initial loss and infiltration loss from the rainfall, total rainfall, and then draw this hydrograph, then you are getting the effective rainfall hydrograph represented by ERH. Okay. Now, this is the end of the first part, that means solution of first part of the problem. Now the second part, solution to second part is very easy. We know that ERH is equals to DRH, that means equals to area of ERH. So what is the area of ERH? In the earlier slide we have seen that at every duration there are bar graph, and bar graph is in rectangular area. So length into breadth will be the area of the one of each of the bar graph. Now there are, I think, 4 number of bar graphs, the other was 0. So find out the area of these 4 bar graphs and add them with each other. For example, you see I have also considered the 0 ordinate to demonstrate it properly. 0 ordinate into 2 is 0. So this will be your 0. Okay, then the first coordinate 0.7 multiplied by 2, second coordinate 0.8 multiplied by 2, third coordinate 0.35 multiplied by 2, fourth coordinate 0.45 multiplied by 2. So these are the area of all the four bar graphs, and when you add them, it becomes the area of hyetograph. Correct? Now my next problem is to find the volume of DRH, which is actually given by area of ERH multiplied by area of catchment, and area of catchment is already given as 5 area of catchment is already given as 5 kilometers square, and you can easily convert it into meter square, but because we are considering the end unit to be meter cube, so this can be converted into what? 5 into 1000 kilometers, because 1 meter is equals to 1000 kilometers. So 5 kilometer will be 5 into 1000 to get the meter. But remember, not only 1000, because this is given in 5 kilometers square. So this 1000, the conversion time will also be in square. So this is actually 5 into 10 to the power 6. Okay, clear? And this 4.6, this is represented in centimeter by adding all the area of the bar graphs. So 4.6 centimeter, and this centimeter must be taken converted into meter, because n is, as you recall, meter cube. So divide 4.6 centimeter by 100. So this will become 0.046. So when it becomes 0.046, it becomes meter. Now this is also in meter square, this is meter. Multiply it, and you will get a value of 23,000 meter cube. Okay, this is 5 kilometers square, so that is why I convert it into 5 into 10 to the power 6 meter square, correct? And this was in centimeter, I convert it into meter by dividing 100 to it. So meter into meter square will be the result, will be in meter cube. The result is 23,000 meter cube. So this is your solution to the second part, and we have already shown the solution to the first part. So you can imagine how easy it is to find the volume of direct runoff with the help of effective rainfall hyetograph and its area. Of course, the area is important. And along with this, another very important term is Phi Index. So with this three data, dr can be found out, volume of dr can be found out with the help of area of ERH, effective rainfall hyetograph, and the value of Phi Index. And another thing is required, duration of storm. That is not the entire duration, but the incremental duration, which is 2 hours in our case. Okay, so first part was to draw the hyetograph. We have already drawn that, as I have demonstrated. In the second part, calculation of volume of DRH, that has also been done. So that is why 25,000 meter cube is the answer. That will be clear, because so the answer is like this: 25,000 meter cube. Okay, so this is more or less the solution to the this problem, which has been taken from Subramanian, uh, Engineering Hydrology by K. Subramanian, and you can find this sum in numerical number 6.3. So here what we have done is we have drawn the hydrograph and calculated the volume of DRH with the help of the catchment area, with the help of the Phi Index and incremental duration, and the entire data of that storm. Okay, so this is a very simple process if you know it. If you do not know it, it is also a very complex process.